Okay, so linear algebra is it's a big subject, and the starting point for us is the study of linear equations. Historically, that's really what linear algebra started out as: the study of linear equations, and more specifically, systems of linear equations. You have been dealing with systems of linear equations since your first algebra course, so this is not unfamiliar territory. But what we're gonna do here is review what a system of equations, what a linear equation is, what a system of linear equations is, how to solve them, and cover some terminology. What this is going to do is lay some groundwork for us, which by section 1.3 will naturally lead us into a discussion of matrices, which is one of the major topics of linear algebra. Matrices are kind of the lens that we view the material of linear algebra through in a lot of ways. The study of linear algebra is not restricted to systems of linear equations. It's just that systems of linear equations gives us some good tools to study the much more abstract concepts that we come across later. So let's start working on just this first topic here. So to begin with, what is a linear equation? Well, a linear equation is any equation that can be put into this form. A1x1 plus A2x2 plus however many terms, u1 until we get to this last one, a n xn equals b. The a's are constants here. The b is also a constant, and the x's are variables. So in the event that b is equal to 0, if this sum of terms here is equal to 0, we say that this linear equation is homogeneous. You're going to see that term a lot in this course. Okay, so here's a few examples. You can look through these of linear equations. This last one here, you might look at this and think that doesn't look like a linear equation, but try multiplying both sides by 2y and then subtracting the 2y from both sides. You end up with x minus 2y equals 0, which is a linear equation because it can be put into this form. And that's the key thing. It doesn't have to start out looking like it's in this form. It just needs to be able to be put into this form to be a linear equation. This here is also a linear equation because if you subtract everything over, or if you subtract the a and add the b over, let me say it that way, you can combine like terms and you get something that looks like a linear equation. These are non-examples of linear equations. This one has a radical in it, and you'll notice that radicals don't appear in this definition for a linear equation. This one's a polynomial. So the variables in a linear equation cannot be raised to any power other than 1. Okay, even though there can be multiple variables in a linear equation, they cannot be raised to any power greater than 1. This one, it has a natural logarithm in it, and that's not something that can appear in a linear equation. So you know what linear equations are from algebra. That should feel very familiar. Systems of equations, namely, if I say that we have a system of m linear equations in n unknowns, then what we're talking about is m equations of this form in a simultaneous system. And when I say simultaneous, what I mean by that is a solution to a system has to be a solution that satisfies every equation in that system simultaneously. We'll talk about solutions in a moment. Actually, we'll talk about solutions right now. This is a general system of equations here. And notice the variables I'm referring to as unknowns. I'm usually going to call them unknowns in this class. Okay. Now, oftentimes, because the topic of systems of equations naturally leads into matrices, we use matrix notation a lot when we talk about systems. In particular, I will sometimes call this system an m by n system. M meaning the number of equations, n meaning the number of unknowns. We know from algebra that a solution to a linear system in n unknowns is something that we call an ordered n tuple. So you're familiar with ordered pairs, which I talk about here, ordered triples as well. Because we're being general here, if we have n unknowns in a system of equations, a solution has to provide a value for each of those unknowns that can be plugged into each equation and satisfy that system. So if we put those n solutions into an ordered sequence like this, we call that an ordered n tuple for whatever n happens to be. Okay. Now, in the case of ordered pairs or ordered triples, there's some geometry that we can associate with those. Ordered pairs we associate with points in the plane. Ordered triples, we can associate those with points in space. If you haven't had Calculus 3 yet, which you don't need to have had for this class, you may not be as familiar working in three-dimensional space and points and vectors and things like that. We do deal with that in this class, and we'll kind of ease into that once we get to that point. But that you can at least imagine an ordered triple as a point in three-dimensional space. Now, let's focus for a moment on just 2x2 systems. So systems of equations where you have two unknowns and two equations. Here's a general 2x2 system. a1x plus b1y equals c1, a2x plus b2y equals c2. You know, again from algebra, that linear equations are called linear equations because we can graph them and their graphs look like lines, which we have some graphs down here. Because systems of two equations in two unknowns are going to be represented by a pair of lines, they're linear equations, so a pair of lines in the plane, we have a few different cases we can look at. In fact, there's 3 specific cases that we're going to break this down into. So first of all, remember, a solution to a system of linear equations has to be, in this case, an ordered pair, because we have two unknowns, and it has to satisfy both equations simultaneously. But what is the graph of an equation? Well, the graph of an equation is just the set of all points, in this case ordered pairs, that satisfy that equation. So graphs, in this case of lines, are visual depictions of solution sets for an equation. Now, if we're looking for a solution to a system, we're looking for a simultaneous solution, which means we need to find a point that's on both lines simultaneously. And graphically, it's easy to see where two lines would contain the same point. We call that a point of intersection. So here, if the two lines represented by the system of linear equations are parallel, then the two lines will never intersect, and that would mean that they have no solution. There's no point that they have in common. If you have two lines that have different slopes, like this, then they're guaranteed to intersect at exactly one point. So in a case like this, we can have one solution to our system of linear equations. The only other possible case for a system of two equations and two unknowns is that the two lines are in fact the same line. These equations can actually look slightly different from each other, but their graph can still be the same line. In those cases, we say that the two lines coincide, or we call them coincident lines, and every point on either line is a point of intersection. So every point on that line is a solution to that system of linear equations. In those cases, we have infinitely many solutions. Be careful with this, because to say that a system has infinitely many solutions does not mean that every ordered pair is a solution. Only the ordered pairs on that line, but there are infinitely many of those. Okay? So with that, let's take a look now at 3x3 systems. And again, if you haven't had Calculus 3, you may not be as familiar working in three-dimensional space. So some of these things, you're going to have to just take my word for it. But whatever the case, this is what a general 3x3 system would look like. Now, in three-dimensional space, a linear equation actually doesn't look like a line. We can graph lines in three-dimensional space, and we're going to talk about how to do that in Chapter 3. But even though it's called a linear equation, in three variables like this, x, y, and z, the graph of this equation actually looks like a plane, not a line. So when we're talking about a system of three equations in three unknowns, then we're talking about three planes if we want to look at them graphically. So just like with the case of lines, or lines in the plane, if we're looking for solutions to a system like this, then we're looking for points of intersection between three planes. Now with planes, there's a lot more different cases to break this down into, but it turns out that even though you can look at all these different configurations for the three planes, it actually boils down to the same three categories in the bigger picture. So for example, in this case here, we have three parallel planes. None of the three planes intersect with any of the others, so there's no hope of having a solution to this system because there's no common point. Here, we have two parallel planes and another plane the third plane that cuts through both of those. This has no solutions either, because even though this plane intersects the other two, for a system of 3 equations and 3 variables like what we have up here, we need a point that's on all 3 planes at the same time. So an intersection between 2 of those planes is not enough. It needs to be an intersection between all 3. Everything in this top row are examples of where we have no solutions at all. Down here, we have some cases where we do get some solutions. Here, these 3 planes intersect at right angles. You can think of these as like the coordinate planes in 3-dimensional space. You can see that they all intersect at this little point right here, giving us exactly 1 solution. Okay. Here's another example where we have solutions. In fact, we have infinitely many solutions. These 3 planes, you can see, all intersect at this line. And we know that lines consist of infinitely many points. So all of the points along this line would be a solution to the system of equations that this represents. Here's another case. All 3 planes coincide, which means every point on any of those planes would be a solution. And then here's a similar case as what we have here. It's actually kind of a combination of these 2 cases. So even though we can break this down into all these different configurations, we still seem to only have no solutions at all, exactly 1 solution, or infinitely many. And what we're going to prove later on is that this is actually going to be the case for any system of equations, any m by n system of equations, a system of linear equations specifically. That's important. Whether it's a 4x4 system, whether it's a 10x20 system, or whatever else you can imagine, you will only ever have no solutions at all, 1 solution and only 1 solution, or infinitely many. Okay, so let's start looking at some examples to sort of see this happening. So to begin with, we want to solve a simple 2x2 system, and this is going to be a review from algebra how we do this. So if I want to solve this system of equations, we can use an approach called elimination, where I want to eliminate one of the 2 variables in this system in an attempt to solve for the other variable. Notice, for example, if I were to multiply this second equation by 2, then my system of equations looks like 3x minus 4y equals 12. And down here I get 4x plus 4y equals negative 6. If I were to then add these 2 equations, the negative 4y and the positive 4y are going to cancel each other. What I'm left with is 7x equals 6. Solving that for x tells me that x is equal to 6/7. Okay, that gives me one of the 2 values that I need for my ordered pair. It's an ordered pair because I have 2 variables in this system. I can solve for the y, the other variable, by picking one of the equations here and plugging the value of x that I got into that equation and then solving the equation for y. So if I chose the second equation here before I multiplied it by 2, that's going to give me 2x, which is 6/7, plus 2y equals negative 3. Now, this is a simple linear equation with some fractions. This is algebra 1 stuff. I'm not going to go through all the steps. I'm just going to go straight to a solution because I know you can do that. Y is going to be equal to negative 33/14. So these make up the solution to this system of equations. And it's the only solution because I found it using a deductive process. That means my ordered pair that I want for my solution is 6/7 negative 33/14. Okay, so there's an example where we have one and only one solution to a system. Let's do some more. All right, here I'm solving another 2x2 system, and I'm going to take the same approach. I want to use elimination. So it doesn't matter which of these 2 variables I eliminate. I just go whichever one seems like it's going to be the easiest. So, for example, I have a negative 4x down here. If I were to make this a positive 4x, then I know those would cancel. I'm going to multiply my first equation by 4. Now watch what happens in this case. I get 4x plus 12y equals 40. Down here, negative 4x minus 12y equals 5. If I add these 2 equations, not only do my x's cancel out, but you'll see my y's are also canceling out. So this whole left-hand side is actually just 0. What happens on my right-hand side? Well, on my right-hand side, 40 plus 5 is going to give me 45. And what we have here is called a contradiction. Contradiction because 0 is clearly not equal to 45. I don't have any variables left, so there aren't any values of x and y that could have been plugged into either of these equations to satisfy both of them simultaneously. That means that if I were to graph these two equations, you're going to see a pair of parallel lines indicating no solution at all. So in this case, we say no solution. Okay? Moving on to this one. This is a 3x3 system. Okay? So in this case, 3x3 systems are a little bit more involved if we're going to solve them using this approach. We're going to talk about a different approach that we can use with something called an augmented matrix in a little bit. But right now, I want to just try elimination. So what I'm going to do is use this first equation to try and eliminate the x's in these two equations. And that requires a pair of operations here. So I'm not going to change my first equation in any way. 2x minus y plus 2z equals 1. What I'm going to do is I'm going to imagine doing elimination on this with this second equation, and I'm just going to replace this second equation with the result. So think about what that would have to be. If I'm trying to eliminate this 4x, then I'd like for this term to become a negative 4x, so I can add it to that and cancel. Okay, so I'm going to do a lot of this work mentally. If this were an Algebra 1 class, I'd have you write a lot more down, but we're going to be doing a lot of this mentally. In order to make this a negative 4x, I'd have to multiply this entire equation by negative 2. So if I multiply this by negative 2 and then add it to this term, I get negative 4x plus 4x, which is 0. That's good. That's what I want. So that's going to make this disappear. I'm not going to write anything quite yet. That negative 2 is also going to get multiplied to negative y, giving me positive 2y, but then that's going to add to my negative 2y, giving me another 0. So my next term is going to be a 0. Not going to write that yet. Notice also, negative 2 times 2z is negative 4z. Adding that to this, again, gives me 0. So I end up with 0 on this left-hand side. If you need to write down all of those steps, feel free to do that. At this level, we can talk through some of those steps. Okay, now I also needed to multiply 1 by negative 2, which is negative 2, and add it to this. Notice this time I get 0 equals 0. This is not the same thing as what we got up here, because that's not a contradiction. 0 does equal 0. Okay, notice if I wanted to do the same thing with the third equation, in other words, multiply this by negative 3 to eliminate the x term here, giving me negative 6x, so it'll cancel, you're actually going to see the exact same thing happen. We end up with 0 equals 0 again. Not a contradiction. So this does imply that there are solutions, and more importantly, it says that there's infinitely many solutions. In fact, what this tells me is that these three equations are going to give me three coincident planes, giving me this case right here. Each equation actually describes the exact same plane. So now the question is, how do I represent my solution? If this were an Algebra 1 class, you would just write infinitely many solutions, but that's not going to work for us. We want to know more about the solutions that we're talking about. So what we're going to do is define a couple of terms here, which we're going to talk about again in the next section. This first variable here, the x variable, I'm going to call that a leading variable, and I'm going to be more specific about what I mean by that in section 1.2. So right now it's just a name I'm assigning to it. The y and the z are going to be called free variables. What I'm going to do is solve this for x. Okay, so if I were to solve this for x, I'm going to get x equals 1 plus 1/2 y plus, minus z. Notice that's just the steps that would have been required to isolate the x here. All right. Now it turns out if I pick any number that I want for y and any other number that I want for z and plug them in here, I'll get a value for x that corresponds to those, and the x, y, and z that result are an ordered triple that would be a solution to this system. But because I can pick any number that I want for y and any number that I want for z, that gives me an infinite number of choices, pointing me towards the infinite number of ordered triples that satisfy this system. what we're going to do here is create a parameterized solution set. And what that means is for each of my free variables, I assign a parameter to it. The parameters are variables as well, and I usually use S, T, R, those letters to indicate those. So if we let y equal the parameter S and z equal the parameter t, then substituting these parameters into this equation tells me that x is equal to 1 plus 1/2 s minus t. I can put all of these in the form of an ordered triple, making sure x comes first, so 1 plus 1/2 s minus t. Y comes next, we define that to be s, and then z comes last, we define that to be t. This is called a parameterized solution set. And the way we interpret this, notice it's an ordered triple. Again, if I plug any number I want into the s's, and then any other number I want into the t's, the resulting ordered triple will be a solution to this system. I encourage you to play with this a little bit. Pick some values and plug them in for the s's and the t's. Make sure you're plugging the same number in for both s's, and then whatever number you choose for the t's, it's the same number for each one. Do that, and then check and see if it actually does satisfy these equations. Okay? But this is better than writing infinitely many solutions because it's telling us what the solutions look like. This is an extremely, extremely important process throughout this course, the ability to parameterize a solution set. We do a lot with this idea here. Okay? We'll move on to augmented matrices in the next section. I'm going to stop this first video here.